We had a few additional questions about logarithms in terms of expanding or condensing them. So let's go ahead and consider a few examples, and hopefully this will help. We need to remember a few basic properties of logarithms in order to expand or condense them. But first, let's think about how logarithms work in general. If you were asked what the log base 3 of 81 were, what would you say? Well, we remember that 81 with a base of 3 is basically 3 to the 4th power, because 3 times 3 times 3 times 3 gives us 81. So what we could do is, if we're answering this question, is we could think about it as log base 3, and keep in mind that 81 is the same as 3 to the 4th power. So instead of 81, we can put 3 to the 4th. So remember we said that a log and an exponential, that these are inverses of each other. So when we combine these either as log base 3 of x, or, when we combine them as either log base 3 of 3 to the x, so again, we're combining the log with the exponential, or if we combine it the other way with the 3 as the base and the log as the power, because they're inverses of each other, when we combine them, when we compose them, we're going to end up simply with x. In other words, these two are going to cancel each other out no matter which way we write it. So notice here that we have log base 3 and base 3. So these are going to cancel each other out. That's going to end up being 4. If you didn't understand that, think about it this way also. When we write a log expression, what are we really asking? We're saying if we have log base 3 of 3 to the 4th equals something, this something is the power. It's asking what is the power. So we know the base is 3. We're asking what the power is, and we're saying that the answer is 3 to the 4th. So in other words, our answer is 4. So suppose that we were asked something else like log base a of a to the 4th power. Well, what is that? So we already know that if a is 3, then our answer is just 4, because these are going to eliminate. But the same thing would apply if we had log base 5 of 5 to the 4th, that these two would eliminate each other, and we'd just end up with 4. So notice that we have the same base here as we do here. So that tells us that these are going to eliminate, and we just have 4 as our answer. So that basically is the inverse property of logarithms, that to evaluate a log, sometimes it's important to think about how you would express the answer part of it to the same base. So let's say that we wanted to evaluate log base 2 of 64. Well, we could think about 64 with a base of 2. In other words, 2 to what power gives us 64? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So we have a power of 6 here. So in other words, 2 to the 6th is the same as 64. So we can think about this as log base 2 of 2 to the 6th, which, as we expressed before, is just going to be 6. Sometimes it can be a little confusing when we change notation. So suppose that we wrote down ln of e to the 5th. Well, first of all, what is e? E, just like pi represents 3.1415, etc. E also represents a number of this type. It's an irrational number. So it'll be 2.7182, etc. When we write the natural logarithm, and of course E occurs a lot in nature, so we can refer to it as natural. So the natural logarithm is a logarithm. That's what this ln stands for. It stands for the natural logarithm. So this is like saying log base e instead of, let's say, log base 3 or log base 5. We're using e as the base. So if we do log base e of e to the fifth, we can just write that simply as ln of e to the fifth. Since log base e has the same base here, then we expect that this would just be 5. So in other words, the natural log of e to the fifth is just going to be 5. We can also say in general that if we have the natural log of e to some power, that our answer is just going to be that power. So suppose that we had an application problem that we needed to figure out. Suppose that we had 5 ln of e to the 3 or e to the third plus ln of e to the second. What exactly would we do? Well, we can apply our properties that we said before. For example, we said that if we're multiplying in the argument, it's the same as adding logs. We said that if we're dividing in the argument, it's the same as subtracting logs. We said that if we had a power in our argument, we can just take that power and bring it to the front. So it's basically the same as multiplying a log by that power. Notice that that's what's happening here. We have this 5 in the front, just like how we have this r in the front. So just like how r log x, we would say take this and put it here as the power. So now we can write it just as log of x to that power. We can take this 5 and put it as an additional power here. So what that means is that now we can write it as ln of e to the third raised to the fifth power plus ln of e to the second. So when we raise a power to a power, we multiply. So it's going to be the natural log of e to the 15th plus the natural log of e squared. Remember this rule? So we know that when we're adding logs, it's the same as multiplying the arguments. So here we're adding the logs, so we need to multiply our two arguments. So if we do e to the 15th times e to the second, what's going to happen? Well, we're going to end up with e to the 17th. So this is all equal to the natural log of e to the 17th. But if we apply our inverse property for logarithms, then we know this is basically just 17. It's basically what we just said before. The natural log of e to the x, no matter what x is just going to be x. Remember that if we had log base 3, and even though we're using 3 here, we could use really anything. But if we said log base 3 of x, this is a logarithmic function, its inverse would be 3 to the x. Remember that if we were to combine these as either log base 3 of 3 to the x by function composition, or if we were to combine it with function composition as 3 to the log base 3 of x, no matter which way we combine it, the two are going to eliminate each other and just leave x. So this is true no matter what base we use, whether it's 3 or 5 or 7, as long as this base and this base are the same, we're going to end up with basically x when we do our function composition. So if we did log base e of x, then what would the inverse be? The inverse would have to be e to the x. So if you notice, we wrote ln every time we had log base e. So this is the same as saying ln of e, ln of x and e to the x. So if we combine these with function composition, what would it look like? Well, we could have either ln of e to the x, or we can have e to the ln of x. And just like before, these two have the same base, they're going to cancel each other out and just leave x. These two have the same base, they're going to cancel each other out because they're inverses and just leave x. So that's important to note, because what if we had the following example? Let's say we had the natural log of 2x plus 5 is equal to the natural log of 3. Well, first of all, we know that 2x plus 5 has to equal 3 because these these logarithmic functions are equal to each other. So their arguments have to be equal. But if you don't understand that, just think about it this way. Let's say that we exponentiated both sides. Think about, what is the base of the natural log? It's e. So if we exponentiate both sides with a base of e, then this e and that natural log, they're going to eliminate each other. And we're just going to be left with 2x plus 5. Same thing over here. This e and this natural log eliminates, and we're just left with 3. So if we solve this equation, minus 5 minus 5, 2x is equal to negative 2, divide by 2, divide by 2, then x equals a negative 1. So condensing a logarithm might be useful just so we can get an ln here and an ln here so we can solve the equation. So let's say that we had something like that, and we're going to go as far as the condensing. The solving, we can leave that for another day. So let's say that we had this particular problem, ln of x minus 3 plus ln, or natural log, of x plus 4. And we want to figure out when it was going to equal 3 ln of 2. Well, we can use our properties. We know that the first property says that if we have multiplication, that it's the same as log plus log. The second property says that if we have division, it's the same as log minus log. And the third property says that if we have a power, we just bring that power to the front when we're expanding it. So we can really use a couple of these to simplify our log expressions. For example, if you look at the third one, it says if we have a value we're multiplying by, we can just bring that into the front here on the argument as a power. So that means this 3 is going to go here as a power. So if we rewrite everything, this would be the natural log of 2 to the third power. If we look at the first property, it says that basically addition of logs is like multiplying the arguments. So notice that we have addition right here. So we're going to multiply the arguments. So we can rewrite that as the natural log of x minus 3 times x plus 4. We can simplify this even further as the natural log of, if we do the distributive property, basically FOIL everything out, we're going to end up with x squared plus x minus 12 And over here, 2 to the third is going to be 8. Just like before, we can exponentiate both sides. The natural log and the e cancel each other out. The natural log and the e cancel each other out. So now to solve this equation, we just need to use what we already know about solving a quadratic equation. So we'll leave that part for another day. But notice that the critical step here was to get all of this right here down to just one logarithm, or all of this right here down to just one logarithm. So that's one of the reasons why condensing is so important. So suppose we're asked to expand the following logarithm. Suppose we have the natural log of m to the fifth over the square root of 7. How exactly would we do this? Well, notice in our argument that we have division. And for what we said before, if we're taking the log of something that we're dividing, that we should be able to split it up as log of x minus log of y. So we're going to split this up as the natural log of m to the fifth minus the natural log of square root of 7. So if we wanted to, the square root of 7, we can write it as 7 to the 1/2. So this is basically natural log of m to the fifth minus natural log of 7 to the 1/2. So this, if we remember, if you have log of something to a power, we said that we can just write it as take that power, put it in the front and as a factor, so it'd be r times log of x. So that means that this 5 here can go in the front as a factor, and so can this 1/2. So it's basically 5 times the natural log of m minus 1/2 times the natural log of 7.